All right, thank you. So it's been a long day, and I'm sure everybody is hungry, which is why I decided to give a lengthy and very technical talk. So hopefully it'll be interesting. And as the title of the talk suggests, I'm going to be talking about delimited continuations. And I'd like to start off just by talking about a little bit of history, because delimited continuations are not a new idea. In fact, they were first proposed about 10 years before I was born. And basically, there was a large amount of initial work. A bunch of people published, mostly in the scheme community, also a little bit elsewhere as well, but they didn't really see very much mainstream adoption. And if anything, I think this sort of confused the situation further, because there were just, you can find a dozen different equivalent presentations, all very, very slightly different with different names, and it's sort of unclear which ones are the canonical ones, which ones add things. So they've been very confusing for a while, but in spite of that fact, recently, a number of programming language communities have expressed some interest in them. And that includes everything from OCaml, which just gained support for delimited continuations in, I think, 5.0. And there was also even some discussion within the Java community about adding delimited continuations, which is pretty mainstream. So the community that I participate in the most is Haskell. And I've been writing Haskell for about 6 years. But I initially proposed adding them somewhere in early 2020. Proposal was accepted. They were in limbo for a while, and then I started at Twig recently, and so now I'm actually working on GHC as part of my job, mostly not things like this, but I did manage to finish them. And finally, as of just a couple months ago, we have support for delimited continuations in GHC 9.6, which is very, very exciting. Of course, it feels a little bit silly to talk about all this, given that I imagine most of the people in the room have absolutely no idea what delimited continuations are, or have maybe a very vague understanding of what they are and don't really know what the details are. So that, of course, is the point of this talk. And my hope is that by the end of this, you will discover that, in fact, they are not this mystical thing, even though people often do talk about them as this mysterious, amazing, sorry, my mic's falling off, expressive thing, but in fact, they're really fairly simple. So we do need to start by talking a little bit about terminology. All right, hopefully that'll stay on. So people, a lot of the time, talk about continuations, and they really are using this as a shorthand to mean maybe delimited continuations, or actually, I think really, first-class delimited continuations. And what we're going to be talking about today are native first-class delimited continuations. So we have all these adjectives in here, which is great. And I mean, I imagine to many people in the audience, these just sound like superlatives, like I might as well just be saying premium, deluxe continuations. But in fact, they are actually important, and we're going to talk about each and every one. But we need to start with the noun here, continuations, since again, I imagine most people don't even know what those are. So I want to start by kind of dispelling a few misconceptions. The first of which is that delimited continuations are a language feature. In fact, in their simplest form, a continuation is really just a concept. And this is fairly abstract. So I think words that I can compare to would be things like scope or value. We wouldn't say that values, that a language having values is a feature. Pretty much every language has values, but value describes a particular aspect of a programming language, and we can use that to talk about it. Additionally, continuations aren't even all that exotic. This is a concept that applies to basically every single programming language that you can imagine. And in particular, it applies to evaluation. So we're going to spend a lot of time talking about evaluation. So just to kind of demonstrate this and make this more concrete, we're going to take a look at this very, very simple arithmetic expression. So if we were to imagine how we would evaluate this, just sort of stepping through it, if we assume just a strict left-to-right evaluation order, then we're going to start by evaluating this sub-expression on the left. Of course, 1 plus 2 reduces to 3. And then we can move on to this sub-expression, 3 plus 4 reduces to 7. 7 times 3, 21, and we're done. Obviously, I don't expect to be terribly controversial. But the point of illustrating this is that at each step, we are identifying some sub-expression to reduce, and then we're leaving everything else the same. And we think about this, or we don't think about this, because it's just second nature. But this process of sort of selecting some sub-expression and reducing it is actually sort of essential to what I'm going to be talking about today. So I want to go back to the beginning and go through it in even more excruciating detail and point out, okay, so we selected this sub-expression to evaluate, and then we had this extra stuff on the right. And so what we're really doing at each step is separating the expression into two pieces. And I've sort of marked the place where we removed the 1 plus 2 with that circle, which you can read as a hole. So that's the hole that we removed that expression from. And then we obviously reduce the bit on the left and plug it back in to that hole. So because we're going to be spending a lot of time talking about this process of splitting things, evaluating, recombining, we want to have names for each of these two bits. So the bit that we're currently evaluating, currently reducing on the left there, that 1 plus 2 highlighted in red, since that's the expression we're currently reducing, it's the reducible expression, we're going to abbreviate that as redox, which is not a term that I came up with, that's a standard term. And so for the bit on the right, what do we call that? Well, we could call it the context, but that would be kind of vague. We could call it the maybe evaluation context. That is actually a term that gets used. But another way to think about it is that it describes how to continue evaluation after we have taken a single step of reduction with the redox. And because it describes how to continue evaluation, we call it the continuation. And I imagine that at this point, some of you are tilting your heads because that seems almost so simple that it's boring. But the continuation, or continuations, are described as this strange and magical, mystical thing. We'll get there, but we're not there quite yet. And this is really what continuations are. So obviously, the continuation, as we're talking about it here, changes with each step of evaluation. It's a dynamic property. So if we continue this evaluation sequence, then we would select the 3 plus 4 sub-expression as the redox now, and the bit on the left is now the continuation. The hole has moved, and again, we can go through that same process and recombine. And then once we have this, then it might seem like, well, we don't have any continuation anymore. We just have a redox. But of course, we can also think of that as just being an empty continuation where the entire continuation is just a hole, and we finish our reduction. All right, so this is what a continuation is. It's very simple. The continuation is just the context in which the thing that we're currently reducing is evaluated. And we can think of that as just an expression with a hole in it. And another way to think about that is that it's a place where we return the value after we've taken a step of reduction. But my favorite way to think about it, and I think the one that perhaps is most interesting but not particularly intuitive, or not the way that I think most programmers would think about it, is that it represents the rest of the program. So it's everything that's left to do is the continuation. And one way to make this really clear is that we can restate the expression this way, where we have exactly the same expression, but we factored out each sub-expression into its own let binding, so that we're just evaluating top-down here. And if we step through this as before, now the hole is just on the right-hand side of that let, evaluate, recombine, and now we just have a let that just binds a value. So we can take this expression, or this statement, and substitute this x, or the 3 in for x, and that statement goes away. And now our continuation has gotten smaller, and it's just these two statements. And so as we step through the program, eventually we could do the same thing here, remove that statement, and you can see that the continuation gets progressively smaller, and it's just everything we have left to do. Now, obviously, if we had some program with a loop or recursion, or maybe it just doesn't terminate, then it doesn't necessarily mean the continuation will always get progressively smaller. But if our program terminates, then eventually, hopefully, well, not hopefully, it will eventually become empty and we'll get a value out. All right, so this is the concept of the continuation. But at this point, you might be wondering, why do we care about the continuation at all? Because it seems so mechanical, this process that I've been describing, that it actually seems boring. The evaluation strategy that I've been discussing is extraordinarily mechanical. We just take an expression, split it into redox and continuation, reduce the redox, substitute it back in, repeat. And so when we look at it this way, it might seem like really the redox is sort of the foreground and the continuation is the background. And obviously we care about the redox, is what we're doing, but the continuation itself doesn't really seem all that interesting. So one sort of, I guess, boring answer is that compiler writers do care about the continuation because somehow you have to keep track of what the program is doing at any given point. But this is sort of a cop-out because obviously most programmers are not compiler writers. And indeed, I think that most programmers don't have very much reason to think about the continuation most of the time. It's just not all that important. But it turns out that there are actually operators, which are frequently used in just about every programming language, that don't play by those rules. And in fact, we can think of them as operations that explicitly exist to manipulate the continuation. One really, really simple example is exit. Of course, exit is a fairly boring function. It just terminates the program. But if we try and think about this in the same way we have been, where we split this into regex and continuation, this clearly does not follow that rule because we're not going to reduce exit to some value and then substitute it into the whole. In fact, we essentially just delete the continuation. So we can think of exit as a function that throws the continuation away. So, okay, by the strictest sense, this does actually is a function that manipulates the continuation, but it's still pretty boring because we don't care about the structure of the continuation at all, so it doesn't seem like there's really any reason to think about it. So we need something that's a little bit more complicated than just throwing it away. We need something that will actually depend on the structure of the continuation in order to really motivate why we want to talk about these. And one example of that is throw and catch. Now, the challenge of giving a talk that's trying to be relatively language agnostic and talking about throw and catch is that every language uses its own syntax for throw and catch. So here's the syntax that I'm going to use. For throw, it's simple. It's just a function. It takes an argument. It raises that argument as an exception. For catch, I'm going to use syntax that, as far as I know, no programming language uses, so everybody will be equally upset with me. And basically, it's just for conciseness, but it just evaluates the body. And if the body raises an exception, then it applies the handler expression to that exception. So the handler should produce a function. And if this is not immediately obvious, then let's just look at an example, and that will probably make it clear. So here we have a simple program with a catch expression, and it just immediately throws an exception. And that exception is then caught by this catch expression, which means that it will recover by running this handler. And since the raised expression is 5, then this overall catch will reduce to 3 times 5. That can be reduced to 15. 1 plus 15 reduces to 16. Make sense? Good. All right, so what happens if we try to apply the same reasoning that we've been using to this expression? Well, we can say throws the regex, everything else is the continuation. We can split these apart. But now it's not immediately clear how we would combine these two things to get that expression that's next in the reduction sequence that we were just talking about. Because, if we actually look at what's going on here, we have this part of the continuation, which is preserved, and then we have this part of the continuation, which is clearly not preserved. So somehow it's not just throwing the continuation away, but it is throwing away a part of it. And it might not seem from this division that this actually makes, or this is a good way to look or understand the behavior of throw and catch, because clearly it slices along some other lines. And that's sort of true, but what we can do is just take a look at the continuation again, and we can note that catch sort of slices the continuation into 2 pieces. We have this inner continuation and this outer continuation. And so we can think of this continuation as a sort of nested set of 3 continuations, like Russian nesting dolls, each one inside of the other. And we can note that the throw discards the inner piece while preserving the outer piece. Another way of putting this is that this catch form delimits the discarded continuation. And so that inner bit in red that we delete is a delimited continuation. Again, remarkably simple. Doesn't seem very fancy. So this is all well and good, but I'm still being fairly vague and hand-wavy, and it's not what I'm talking about here is not very precise, and we're not really able to compare all these different things. And it would be really nice if there were some way to do this that didn't involve stepping through, a million examples. So it is now the point in the talk where I get to introduce some notation. And I know that every single time anyone does this and starts throwing math on the screen, there's a portion of the audience, their eyes glaze over. I'm usually one of them. And they say, well, I'm just going to tune out until this part of the talk is over. But I'm only going to introduce 2 pieces of notation. And they're going to be fairly important. So please try to stay awake. So the first one is just this, A arrow B. And you can read this as A reduces to B. And the purpose of this notation is that we're going to describe precisely how we're allowed to reduce expressions so that we can just kind of illustrate what reductions can take place and compare them to each other. So here's an example. This is a reduction rule that says not false reduces to true. Again, probably not very controversial, and we can also have not true reduces to false. Now, these are really boring reduction rules. So a slightly more complicated one looks like this. If true, then E sub 1, else E sub 2 reduces to E sub 1. And this can be read as if the condition in the if is true, then we take the then branch. Similarly, we can have the same thing, but the condition is false, and that reduces to E2, because we're taking the else branch. Make sense? All right, so this is all well and good, but it leaves us with a problem, which is, what if we have this expression? If not false, then 1, else 2. Well, now, this expression doesn't match any of the rules we've given so far. Obviously, based on everything we've been doing in this talk, it's pretty obvious that if we have this expression, we can divide it into a regex and a continuation and split them apart, and now this rule applies to the regex. And then we can reduce the regex, substitute it back in, and now the result matches that if true rule. So we could just say, well, we'll just let these rules apply anywhere in the expression, but that's not very helpful if we're trying to distinguish between these sort of different, when we have operators that don't follow that rule. So we want to be very, very explicit about this. So we're going to replace this rule with a slightly more complicated rule, and this is the piece of notation, the second piece of notation and last piece of notation I'm going to introduce. And it's just this E brackets thing. So here, E stands for some arbitrary continuation. And you might ask, why is it E and not C? I think there's some reason. But people usually write E, and so I'm going to write E. I think maybe it stands for evaluation context. But the important thing is that E brackets X just stands for the expression formed by plugging the hole in that continuation E with X. So to illustrate this, we might have this continuation for E. I changed this to an X on this slide, and I forgot to update that. But that should say X equals not false, and E brackets X equals if not false, then 1 else 2. Make sense? Question? Oh, okay. No question. Great. So why bother with all of this machinery? Well, the reason, as you may be able to predict, is that this allows us to now describe what exit does. Exit looks like this. We have a continuation on the left-hand side, but after we take a step of reduction, it goes away. So exit discards the continuation. Again, not very interesting, because exit is not very interesting, but we can now compare it to the reduction rule for catch and throw, which, again, I know looks very, very scary, but it's not. So let's break it down. We now have 2 continuations, so we're going to distinguish them with subscripts. And this outer one, which again in that example from a few slides ago is that 1 plus outside the catch, that is present to the left and to the right of the arrow, so it doesn't change. And then we have this inner one, which is only present on the left, because that's the portion of the continuation that evaluating the throw throws away. And then we continue execution by applying the handler function to the thrown exception. And that describes the semantics for throw and catch. Now, remarkably, we can actually describe lots and lots of operations this way. And this is very nice because it's very concise. We can compare them to each other. And some operations that, and I'm not going to go through and list a bunch of rules here because I don't think that would be very interesting. And a lot of operations are more complicated than throw and catch, so they're not quite as nice on the slide. But some operations that can be described or can be thought of in a similar way, for example, coroutines in Python, generators in Python, rather. You sort of yield, which is kind of like a throw, except that then you can resume later. And so you can kind of imagine thinking about those in a similar way. So delimited continuations, also an idea, and very, very or they can describe lots of these interesting control operators. So we've now talked about continuations, and we've talked about delimited continuations, and still nothing I've talked about I think is really particularly complicated, but it's also maybe not particularly interesting. So it is now time to take a look at first-class continuations. And this is, I think, what people are usually referring to when they just talk about continuations, and they say, oh, they're so expressive, and you can implement everything with them. They're talking about first-class continuations. But just with everything else, they're not actually that mystical. And so we have to start by answering this question. What makes something first-class? So when we talk about first-class functions, what do you mean by that? Well, we just mean that functions are values in our programming language. So for example, we can pass functions to functions, or store them in a variable. So first-class continuations means that we're going to be able to manipulate continuations as values in our programming language. But of course, what does that mean? Continuations are this thing that we've been talking about so far. It's not really clear how we could turn a continuation into a value, or what that would even mean. Well, if we take a look at these three continuations, can anyone guess how you would turn each of these continuations into a value in some mechanical way? Definitely some correct answers in there.
Wrap them into function?
Yes. Not exactly particularly difficult to guess. This is an expression with a hole, and so we can plug that hole mechanically by just sticking a variable in there and then quantifying over it, capturing it with a lambda, and now we have three functions. So a first-class continuation is just a continuation that's been reified as a single argument function. Of course, this doesn't answer the question of how would you actually obtain such a function in the first place. So the sort of classic approach to doing this was called callCC, which stands for call with current continuation. And it's an operator with a reduction rule that can be described sort of like this. This is not entirely accurate, and I'll get to that in a second. But the idea is that callCC is a function that takes a single argument, which is a function, and it applies that function to a function, which is the reified current continuation, represented by E here. So what this is essentially doing is, as the name implies, reifying the continuation as a function, passing it to the function that you apply to it. So there's sort of this weird inversion of control, but that's essentially what happens. The problem, well, there's a few problems with this. The first is that because the E still exists on the right-hand side, we are duplicating the continuation, and every single time you apply that, you're just going to be sort of appending it to the current continuation. So in practice, what happens is normally callCC implementations, when you apply the continuation, it actually replaces the continuation. And this is just kind of difficult to reason about. And I think a lot of the time when people encounter callCC, it just ends up being confusing. Another issue is that we've been looking at these really, really cute, simple, tiny, self-contained continuations, but really, real continuations don't look like this. They're complicated. And sort of at the root of them, there are things like, shut down the process. And you probably don't want to be capturing that as a part of capturing your continuation. So we need a little bit more control over what we're capturing. Yes, sorry.
So just go back to your last slide. With the E's.
Oops, I'm hitting the wrong button.
Forwards. Yeah, going wrong way, yeah. Okay, so the question is, how big is that E? Right, does it, in some sense, need to be maximal?
Yeah,
right.
For callCC is undelimited, so it's the entire continuation of the program, which is why it includes things like exit process. And indeed, in real systems that implemented callCC, they did not really include exit process. There was actually sort of, they would implicitly capture up to some points. And as it happens, I wasn't going to mention this in the talk, but it's actually a very good segue. This was developed in the context of scheme systems, and they would capture up to sort of, if you can think of the caret of the REPL prompt. And they wouldn't capture the REPL itself, because then you would be, you would no longer be in the REPL. So for that reason, when Matthias Felleisen introduced delimited continuations, the delimiter operation was called prompt. And this is extremely confusing and means almost nothing today, but that's the name that was chosen for that reason. So the delimited version of callcc, originally called prompt and control, and it has a reduction rule which looks like this, which again looks kind of scary, but it's actually very simple. So again, we have, just like for throw and catch, we have this outer portion of the continuation, left alone doesn't change. Then we have this inner portion of the continuation, but now, unlike throw and catch, it does appear on the right-hand side, but appears under this lambda. So we're removing it from the sort of immediate continuation of this expression, but we are just sort of suspending it by reifying it as this function and passing it to the argument to control. So what does this actually look like? Let's go through an example. So here we have this outer portion of the continuation, the inner portion of the continuation, and we have the function that's being passed to control, which will receive the captured continuation. So we're going to split all of these apart so we can look at them independently. And the way that, again, prompt and control work is we're going to take that second bit in red, and we're going to turn it into a function and pass it to the third bit in blue. And then we're just going to put the green part back, and that's all that these operations do. They just rearrange some things. So if we then actually take a look at, okay, so that's one step of evaluation, and then we keep going, then what we need to evaluate are these applications of k, and k is now just an ordinary function. It came from that bit of the continuation we captured, but now there's nothing special about it. It's just a function. So it just multiplies its argument by 2. 3 times 2 is 6. 5 times 2 is 10. Then we do the arithmetic and get 17. Does that make sense? Good. All right, so if you really step through this, you can kind of see how it all works out, and it's really not that complicated. But nevertheless, I found that it is really confusing to reason about. And for a long time, I was very confused that it was so confusing. Because if you look at the reduction rules for throw and catch and prompt and control next to each other, they look really similar. And I have a pretty good intuition for throw and catch, I think. But for prompt and control, there's something that bends people's brains that makes them difficult to understand. And I think I finally, eventually, figured out what it is. So if you look at these, you'll see that mostly they are the same. Catch and prompt, they're the delimiter. Throw and control, there's the thing that causes part of the continuation to be discarded, essentially. And then on the right, we have, we continue by applying a function. But there's a crucial difference between these two reduction rules. For throw and catch, that function appears in the catch. But in prompt and control, it's an argument to control. So essentially what's happening here is it's like if when you handled an exception, the exception handler was specified at the point where you throw the exception, not where you catch the exception, which I think is not very useful, personally. I don't know about you. But because of this, it's very confusing, and what's sort of weird is that it doesn't really have to be this way. We could imagine some hypothetical third set of operators that are a hybrid of the two. So in this case, like throw and catch, this yield operation, and I've just chosen these names arbitrarily. These don't correspond to anything in the literature as far as I know, but it just raises a value, like throws an exception, and the function itself appears as an argument to this delimit thing. But like prompt and control, the handler receives the continuation that was discarded as an argument. So in a sense, these operators implement resumable exceptions. And I think that's actually a pretty decent intuition for first-class delimited continuations. They allow you to do things like throw and catch, where you discard a portion of the continuation, but you're allowed to retry from the point of the throw later. And in fact, because it's just an ordinary function, you're allowed to retry from the point of that throw multiple times. So you can explore like multiple universes. Like if you want to do a search of some kind, you could yield and then resume once with true and once with false and take two different branches, and they would go off and do their own thing, which is interesting. So just for completeness, let's just demonstrate the previous example in terms of delimit and yield. It's essentially going to work the same way. We have this yield sub-expression, which is the regex. We have this handler here. And in this case, I'm just yielding unit the empty tuple because I don't actually want to be yielding anything interesting. But then it does receive the sort of resumption as k. So we can go through the same process again. We have the inner and outer continuations. We have this handler, split them apart. And then at this point, everything is exactly the same. The only thing that's different is where we specified that handler function. And of course, in this example, it doesn't seem like that big a difference because they're very tiny examples. But of course, as you know, in real programs, normally the throw and the catch are not right next to each other. They're usually very far apart. Otherwise, I mean, I guess people do use throw and catch for control flow. But normally people say that that's a bad idea. So in real programs, this difference does make a big difference. So that sort of raises the question of why do you see everything in terms of prompter controller, or maybe more commonly these days in terms of shift and reset. Like I said at the beginning, there's like a million different versions of these operators. And shift and reset are essentially the same as prompt and control. There's a very, very minor difference. But they just don't seem as useful or as easy to understand. And I think there's a few reasons for that. So the first is that in some sense, prompt and control are simpler. Because you have to understand that these were being sort of studied academically as this general control operator that can represent all these things. Because you can use this to implement exceptions. You can use this to implement coroutines. And so just having something that really distills that out was useful. But also there's the historical reason of call CC takes a function to receive the continuation. Control takes a function to receive the continuation. But I think maybe the most compelling to a modern audience is that it turns out that yield and delimit are actually fairly complicated to statically type. And if you go down that route and you really seriously try to figure out how to statically type them in a way that would be useful, you will invent algebraic effects. And I'm not going to talk about algebraic effects in this talk because there's already enough going on. But if you're interested, there's plenty of information out there about that. But I do want to talk a little bit about types in the context of prompt and control because you've probably noticed I haven't talked about types really at all. And some of you may be confused or even annoyed that that's the case. But there's a reason for that, which is that giving types to these operators is still not trivial. In fact, that's true even for just exceptions. We don't really think about it all that much, but if you think about the type of throw, well, it returns anything. This is some universally quantified variable. That's not too big a deal, but exceptions, even in statically typed languages, are usually, to some extent, dynamically typed. You can just throw any exception, and there's maybe some exception hierarchy, and then particular catches will perform a dynamic check to determine what the type is. And maybe that's fine, but then we look at catch, and then catch has to do some kind of typecast, and obviously there's ways that you could have checked exceptions or use some kind of parameterized monad or whatever you want to do. And then you could restrict the type of exceptions to some concrete type. But it's certainly not trivial to do this, and it complicates things a little bit. But this is even more true. This is even more true once we start looking at things like yield and delimit. So in this particular case, yield and delimit, we can give them types, but there's a problem now, because in the type of handler, we have the continuation, but this continuation represents this, oops, I'm hitting the wrong buttons. This continuation represents this E2 here, and the type expected at that point, which again is the type of that yield, depends on the context in which the yield is used. It's in the return type of yield. So that a variable there is essentially out of scope in the type of handler. So we would need some way to relate these things, to connect these things, and even if we did, even if we included that in some ambient context, then then it still would fix it to a particular value, even though really it depends on the position the yield is used. So then you would only be able to use yield if in places that return specific types. And maybe that's okay for you if you're implementing coroutines. That might be fine. But in general, it restricts things. Now, the B type here is not actually a problem. That's fine, because that's just local to this delimit form. That's whatever is expected as the argument to E1. So that's not a problem. But the A really is a problem. So if we take a look at prompt and control, we can see that the problem is still there to some extent, but it's sort of flipped. So prompt here, I'm going to use B still to refer to the outer type here. And control now has a type that looks like this, which is probably the standard confusing type that you often see people use or present, and it doesn't mean very much, to be honest. And here's the reduction rule. And we can see now that, again, this part of the type for control corresponds to that captured continuation. And A is no longer out of scope here, because it's now specified locally, like the function that receives that continuation is now local to E2, which is what's determining that type. So A can be different for each use of control, and there's no problem anymore. But B is still out of scope now. So we've just flipped the problem, because now the function is at the point of the control, not the point of prompt. And so whichever way we do it, wherever we put F, we run into, it seems like, the same problem. So one solution to this is to introduce prompt tags. And this is actually what we have done in GHC. The initial version of my proposal did not include this, and it was just wildly unsafe. And Simon told me that that was not acceptable, which was a good comment to have. So we introduced prompt tags. And the concept of prompt tags is that you just have some value that you can create out of thin air that represents just a tag. And the only thing you can do with those tags is compare them to each other. So you can say, is this the same tag as something else? But they're indexed by a type variable. And that type variable corresponds to the return type expected by the prompt. So then when we apply control, we also pass it the same prompt tag, and that argument to the prompt tag is a witness of that B type. So it connects, it propagates the type information from the location of the prompt to the location of the use of control. And our reduction rule changes slightly so that the control is only matched by prompts that have the same tag. So this provides perhaps the added benefit that you can, much like when you throw an exception, you can only have it be handled by a catch handler that pays attention to exceptions of that type. Then here you can have different prompts with different tags, and you can just say, I want to capture up to a specific prompt with this tag. So again, here's the type of the continuation, and this B parameter connects all of them, and the type system will just ensure that it has to be the same. Now, of course, if you're using some ML-like language, then you have to have some monomorphism restriction in the same way that you have to have some restriction on, say, ref cells. But if you use those languages, then you already know what I'm talking about, and if you don't, then you don't care. So we've now covered first-class continuations, and we've sort of talked about how, this is this very general, very expressive thing. You can get a hold. It's this weird, reflective, high-level operation. You can get your hands on the computation itself. And this seems like it must be very slow. But in fact, remarkably, it's not. There's a way to implement it that is quite fast. So let's talk about that. So how do we implement this? One option would be to use continuation passing style. And this is all right. This is something that Haskell programmers have done in the past. You have some monad that has the ability to basically just threads the continuation through everything. And this works OK, but it is slow. And if you're interested in why it's slow, I gave a talk about that 3 years ago in the context of Haskell. So I'm not going to talk about it today. But it does have significant performance overhead. So the second option is to bake them into the runtime in some magical way that makes them fast. And it may not be obvious what this is. However, as it turns out, if we take a look at a continuation, there's another way to view it. Rather than just viewing it as this sort of monolithic continuation, we can view it as, again, a stacked sequence of nested small continuations. We might call these continuation frames. So each one is a continuation that cannot be composed or decomposed any further into smaller continuations. And as it happens, this is a call stack. I think a lot of the time when people think about what does a call stack mean in the context of functional languages, they don't think about it too hard. But in fact, if you have some expression-oriented language and you have a bunch of different things to do, then you have to store that somewhere, and we store it on the call stack. So in a very real sense, the call stack is the continuation. So what that means is if we have our abstract machine here, and the red X is a use of control, and our continuation is represented by this stack, then we can implement it by just walking the stack. So we look at this frame, and that's not a prompt. We look at this frame, and that's not a prompt. We look at this frame, and it is a prompt. And in fact, it has a matching tag. And then all we have to do to capture the continuation is copy those stack frames into the heap. And then we can just remove them from the stack, and we can also remove the prompt frame. And now we reduce our use of control. We're going to apply that G to the continuation. So we're just going to apply G to some new value, heap object, that we've created. And from the perspective of the program, it's just a function. But from the perspective of the runtime, it's a very special function, which is actually represented by that chunk of stack frames. So when we then, if we imagine that G is just a function that immediately applies this continuation to some value, when the function is applied, we're just going to do the reverse process, which is we just copy the stack frames back onto the stack. And now we can resume from there. So continuation capture and restore is literally just memcopy, which is surprising because, again, this is the super high-level operation that is manipulating something that doesn't seem very close to the machine, and here we're very, very low level. We have operations for directly manipulating the call stack, and I think that's pretty neat. And again, maybe these aren't the most useful things to be used directly, but they can be used as a building block to implement all these different things from coroutines, search, exceptions, and in a fairly efficient way. I mean, this isn't all that different from the way that exceptions are implemented in lots of languages, just scanning the stack. Now, of course, memcopy does have some overhead, so it's not free, but it turns out that modern computers are pretty good at doing block copies, and these continuations are normally not very big. It may seem like, okay, well, what if I have a lot of code, and then I have to store some really big continuation? But of course, keep in mind that on a real system, you're not literally storing the code on the stack, you're storing pointers to frames of code. So it really just depends on the nesting depth, and usually that doesn't get enormously large. So that's an efficient way to implement native delimited continuations, and it's not much more complicated than that. So just a few miscellaneous details before we wrap up. If you have specific constraints, and for example, you know that the continuation will only ever be invoked exactly once, or at most once, then you can avoid doing certain copies and things like that, which makes things more efficient. And in fact, OCaml, I believe, does have one-shot continuations, so they can just move memory around, doesn't have to do quite as much copying. Another thing is that I implemented these in Haskell, and Haskell's lazy, but we've been talking a lot about evaluation order, but it turns out that, I guess you could probably come up with some way to generalize this notion of continuations to a lazy language where there's like some non-deterministic, you have a tree of you could do it. Maybe someone already has, probably someone already has, but that's not what I'm talking about, and that's not what I did. So we just use monads, and it all works out. So then, obviously in reality is more complicated than this, but it turns out remarkably not that much more complicated. In the implementation that we did in GHC, we had to worry a little bit about saving and restoring certain flags pertaining to async exceptions. And then, of course, obviously, you have to worry about Stack Overflow scenarios. And in theory, there could be performance pathologies. Hopefully, people will find them and then report them as bugs. We'll see. But remarkably, it is mostly just memcopy. It really is mostly just memcopy. I'm not exaggerating that. And one problem here is that we do really severely lack continuation benchmarks. So it's hard for me to say concretely, is this better than continuation passing style all the time? One thing that's interesting is that since you're doing a block copy, whereas CPS, this is kind of getting into the weeds, sort of creates a like persistent data structure out of the continuation frames, and so you can have sharing, and so maybe there's some situation. I've said to many people over the years that there's probably situations where CPS is better. I've never actually seen such a program, but I would love to see such a program. So if you find such a program, please tell me, and then I can include it as an example in my talk. All right, now one final thing is that sort of the unsung hero, which I've barely discussed in this talk, is reduction semantics, which is this style of talking about the evaluation of programs as just a sequence of reductions. It's sort of like the simplification you learned in grade school algebra. And what I really love about this is that it allows us to talk about all these things, and at no point do we have to talk about an abstract machine. At no point do we have to talk about registers, memory, heap. Obviously, when we were talking about the implementation, we did a little tiny bit. But every intermediate state of each of those reductions is a program. You could start evaluation from there. There's no context to restore, and it just works. And this gives us this nice equational reasoning, and we're able to reason equationally in terms of the source code about these really complicated control operators, which do interesting and complicated things. So if you're interested in learning more reduction semantics, small step operational semantics, you can look up those terms, and there's lots more there. All right, so we have now covered pretty much all these things, and I imagine that many people will look at this and say, okay, well, I don't have all 4 of them, so this talk is mostly just academic to me. But because of that nice reasoning framework, I think it's worth saying that it's still a useful way of thinking about programs, even if you have a language that maybe only has these first 2. So don't write them off, and it's still an extremely useful way to think about programs. All right, so that's it. Just to recap, continuations, concept that arises naturally in evaluation. We have these special operators that allow us to manipulate the continuation. And first-class continuations just allow us to take that continuation and get our hands on it as a function, which can be used to implement all sorts of different things. And remarkably, this corresponds to low-level operations for manipulating the call stack, which is one of the reasons that I think it's compelling to have these in programming languages, because it's actually not, it's not complicated to implement, doesn't have all that much of a maintenance burden, and it lets people do a lot of really cool things. So it's really exciting that we're starting to see them percolate into these other languages. And that's it. That's all I have to say. Thank you.
Thank you very much. I think I got most of that. Definitely the recap at the end was helpful. There was about 10 minutes in the middle that I think I was over my head slightly. We have about 20 minutes left before we embark on the scavenger hunt towards the party. Does anyone have any questions?
Thanks for the talk. How does this relate to one, go-to statements, and 2, to implicits or like evidence, like you see in Scala or in Aaron's?
Sorry, after go-to statements, what did you say?
Implicits.
Implicits. Yes. Both good questions. So go-to statements, I would say that undelimited call CC is, in a sense, closer to go-to statements, because as I was sort of alluding to, I didn't really want to go into too much detail because I think it might have been more confusing than helpful, but call CC normally, you capture sort of, when you call it, you get a label to something that means, right here in the program. And then when you invoke it, you jump back there and you throw everything else away, which is closer to how goto works. It's still different in that, like, a goto lets you do a forward jump before you've even gotten there. Call CC doesn't, so you have to have the continuation available before you can capture it. And then another thing is that the goto doesn't keep track of any sort of intermediate frame. So like if you have a sequence of functions, if you have a function that calls a function that calls a function, and then you capture the continuation, then you're keeping track of all of those, where if you just do a goto into that location, it's just a jump. So they're more structured, and delimited continuations don't do that, like throw the current context away. So I think then the comparison is a little more stretched. But there is certainly some similarity. As far as implicits go, I don't think there's any super direct connection, but it is a very well-known result, it's been known for a long time, that monads and continuations are mutually expressible. So you can express one in terms of the other, And you can then, obviously the reader monad and things like that can be used to implement implicit-like things. So maybe that answers your question.
So Alexis, you've described a pretty powerful hammer that you've put a lot of work into implementing in GHC, but you haven't had time to describe many nails that you can bang in with this hammer. Would you like to just quickly take a moment to sketch some of your favorite nails?
Yeah, so I do essentially, the original motivator for implementing these was to implement algebraic effects in Haskell in a way that's, I think, both easier to understand and much more performant. And I do have like a half done, or maybe even 80% done implementation of algebraic effects in terms of these primitives. I need to do the other 80% now. So that's the main one that comes to mind. I do know that someone discovered, they mentioned at one point that they were using them to implement like lazy byte string building in an efficient way, which I'm going to be honest, I don't even know, I can't even imagine what that could have possibly meant, but it sounds like somebody else has figured out something to use them for.
There's a question over here and then here.
Thanks for the talk. So I have a question about, do you think the main consumer of this primitive is a library user, or do you think is merit of creating some sort of syntactic sugar that akin to do notation to the monad or applicative do or this kind of thing in Haskell context?
Yeah, that is a very good question. I think that the operations themselves are probably most useful, especially in say, the context of Haskell, where, again, adding types requires a little bit of extra machinery, or at least adding types in a satisfying way. So in that case, they're most useful to a library user. Incidentally, I wasn't going to mention this, but my slides are implemented in Racket, which is a dynamically typed programming language. And the framework that I use to generate my slides uses delimited continuations directly. So it's certainly, they are useful. But I guess the other thing is that algebraic effects, I think in some respects can be seen, as I sort of said, as a typed interface to delimited continuations. And the way that you reason about them is very much the same as the way that you reason about delimited continuations. So I think understanding how they work is still very useful, but maybe using them through a slightly nicer interface is how most people would prefer to interact with them.
Hi. I have one question. So when you have the stack being moved onto the heap, were there any problems? Because I know similar approaches had some problems with like garbage collection and stuff. How does that work with the Haskell's garbage collector? And were there any problems there on the performance and correctness side? Thanks.
Yeah, so the question was, were there any issues implementing that moving stack frames around in the heap? I originally expected that there would be more issues, but as it turns out, GHC already had to store stacks in the heap sometimes for a mostly unrelated reason, which is that to implement laziness, Haskell supports asynchronous exceptions, which means someone hits Control-C while something's being evaluated. You need to suspend the computation of that pure computation and then resume it later. And so there was already some code for doing this in the context of evaluating thunks. And so the garbage collector was already set up to handle that. Obviously, if you have a language that doesn't do that and has lots of mutable references into things on the stack, then that wouldn't be as easy. But in GHC, it was actually pretty easy, yeah.
So the examples you gave us, they look like data is flowing one side to the other. How does it relate to statements that can branch off, like if then else?
How does it relate to state, did you say?
The statements that can branch off.
How does it relate? It can branch off?
Yeah, like conditions.
Well, I mean,
how would it look like?
Here, well, okay, I can't skip. If I had this slide somewhere back here. Okay, it's a ways back. I have 293 slides. Oh, I passed it, yeah? Or no, I didn't pass it. No. This is the slide I was looking for. So I mean, here's conditionals. If it's true, it reduces one way. If it's false, it reduces the other way.
Yeah, but it's like the if reduces, but can we apply the same prompt control to implement if, for example? Or it's just a different pattern?
I'm not sure I entirely understand your question. I'm sorry. Can you rephrase it slightly?
Okay, so we can use prompt control to implement try-catch.
Yeah.
Can we use prompt control to implement if
I
and
see.
else?
Okay, sorry. I must have misheard. Can we use prompt and control to implement if then else? I suppose you can, but the reduction rules for if then else don't use the continuation in any interesting way. They're like for not false and not true, where we just add e brackets around the left-hand side and the right-hand side. So I mean, you could capture the continuation and then immediately invoke it. That wouldn't be very interesting. So I mean, it is interesting in that you could, I actually, while I was working on this talk, I was thinking maybe I could say a control operator is a thing that manipulates the continuation. But then I was thinking, well, okay, but if then else is probably a control flow operator and it doesn't manipulate the continuation. So maybe that answers your question.
Hi, thank you for the great talk. So 2 questions. First of all, am I right to assume that I can use the continuations machinery from GHC Haskell code using shift and reset functions? And second question, do you have an intuition, if that's correct, of course, do you have any intuition how those relate to the operators you presented?
Yeah, so you could certainly implement shift and reset in terms of the operators implemented in GHC, because the ones that I did implement in GHC are sort of the most general form of those operators that can implement all the other zoo of operations. In fact, technically, those operations are normally called prompt 0 and control 0, which is what, again, there's too many of them. There's really, if you go digging, you'll just be lost for hours and hours. The only difference is that the traditional prompt and control actually, on the right-hand side, the prompt stays, and in shift and reset, the prompt stays around both the continuation that's left and the continuation inside the function. But if you just don't leave the prompt in any of them, then you can always put it back if you want. So you could implement it that way. In terms of how it would compare to, like, say, you know, the CPS implementation, were you asking that, or is it just saying? Shift and reset. It's just how would prompt and control compare to shift and reset? Yeah, it's just, that's the difference. It's just one of them leaves the prompt behind when you capture and one of them doesn't. And you can implement shift and reset in terms of this.
So I would have wanted to ask you, what about lazy evaluation? You did say a little bit about that. But I'm imagining now, if you're copying the Haskell stack, on the Haskell stack you have function frames, of course, but you also have update frames. So when you copy the stack, you may be copying update frames. And if you resume those stacks more than once, you may overwrite the same thunk with 2 different values. And now my head just exploded.
Yes.
Do you prevent that from happening, or
yes.
Or what?
That's
How?
a good question. So I'm going to give a slightly more Haskell-focused version of this talk at Zurahack next week. And I actually wasn't thinking about including that, but that's a great thing to include, so thank you. But I can answer it right now, which is that in the implementation, we say if there's an update frame somewhere on the stack, then that's just an error, and we report a compile time error. And to think about what this means from the perspective of the programmer, we demand that prompt and control both exist in the same strict state hash thread. So if they're both in I/O, that's okay. And if they're both in the same use of strict run st, then that's okay. But if you have like unsafe perform I/O, or if you have like prompt, then unsafe perform I/O, and then control, then you'd be capturing through this unsafe perform I/O frame. And that doesn't really make all that much sense because the continuation at where that is eventually evaluated isn't clear. So in order to ensure that the semantics is predictable, we demand that that's never the case.
I would like to ask a question, please. So what do you think are the current limitations in other programming languages? Like, what's the reason why this type of continuations aren't really implemented in other mainstream programming languages?
Yeah, that's a good question. So in the context of OCaml, I know that one of their major motivations is that they wanted to have more control over, basically, user control outside of the core of the language over thread scheduling. Because if you think about the way that a thread scheduler works, it periodically suspends threads and then switches to another one and resumes it. And that's why they implemented one-shot continuations, where you can suspend the computation and you don't have to copy it if you're just going to resume it again later exactly once, because then you just suspend it, you move it somewhere else, you swap another thing in, it runs for a bit, and then you swap them. So that's one example, and that is essentially a form of coroutines, which I mentioned a couple times. Another case, which, to be honest, is also really a form of coroutines, but async await, things like that, they're also, they have a similar behavior where there's basically this cooperative multitasking. In terms of other languages, I do think there's sort of the algebraic effects use case, where you want to implement all these different things, state, reader, exceptions, have a general framework. And then there's lots of things that use coroutines. I don't know off the top of my head if there's some other fancy use that isn't subsumed by existing operations like throw catch, but those are the main ones that come to mind.
Alexis, when you introduced your delimited tag, your typed delimiter tag, you presented it as a kind of side-effecting operation. I think you said it was sort of unit to delimiter tag of B. I was wondering, why didn't you build that in? And that also means that you, in principle, could have many prompts with the same tag and so why didn't you build all that tag generation into prompt itself, so it generates its own tag and passes it to the thing inside? That seems more obvious, but you chose something different.
It doesn't surprise me that you would say that it seems more obvious, because you are a co-author on a paper that presents a primitive that does exactly that. I don't know if you remember. Somehow I suspected that might have been the case. So why not just make it so that the prompt operation takes a function that receives a tag that's just some fresh tag? So there's a couple of reasons. One is that makes the types a little more complicated, because now you have this higher rank polymorphism, and this presentation doesn't need, because then you have some, although I guess it's not actually, because it's not quantified, it's just the type of the return type. But then in that case, what happens if the prompt tag just gets returned by that, right? Escapes that scope. Do you allow that? Do you not allow that? There's not really any reason to not allow it. It's perfectly fine. And having the ability to have the same prompt tag that's used for many prompts is useful in the same reason that having many exception handlers that catch the same type of exception is also useful. So decoupling them, you don't lose anything, and it lets you be a little more flexible.